This video is the first of a new series looking at non-convex polyhedra. We're going to start with an experiment. We'll take a dodecahedron and move each face inwards towards the centre. Initially, although this makes intriguing patterns, it's no longer a polyhedron, because the pentagon edges no longer join up. But let's keep going and see what happens. The faces pass through the centre and start moving outwards on the other side. Then something remarkable happens. The edges start to join up again. If we stop moving at precisely the right point, all edges join up, and we end up with a new polyhedron. It has identical regular faces, edges and vertices. So, is it a new platonic solid? Well, no, it isn't, because it isn't convex, but it's very close. This polyhedron is known as the Great Dodecahedron. Non-convex polyhedra like this, with faces passing through each other, have a more complicated structure than convex polyhedra, some of it hidden from view. If we show a cross-section, we can see some of this hidden structure, with faces passing under and over each other. A line from the centre, marked with a dot, to the outside, must pass through three faces. For example, this line passes through the brown, blue and green faces. This one goes through the red face, then the purple and brown faces simultaneously. So the centre of the great dodecahedron is surrounded 3 times. You say it has a density of 3. A convex polyhedron, on the other hand, always has a density of 1. Note that points away from the centre can be surrounded less than 3 times. For example, this point is 2 faces away from the outside, and this one only 1 face away. Let's try the same thing with an icosahedron. Again, we move the faces inwards, all the way through the centre and beyond, and they join up again at a precise point. We have another new polyhedron with identical regular faces, edges and vertices. This is the great icosahedron. It's more complex than the great dodecahedron, with a density of 7. These 2 polyhedra, the great dodecahedron and great icosahedron, were discovered by Louis Poinsot in 1810. If we start with an octahedron, again, the faces move inwards through the centre and join up again. At first, this looks like another new polyhedron, but if you examine it closely, you'll see that it's actually just 2 intersecting tetrahedra. Such combinations are called polyhedron compounds. This one is called the stellar octangular. The compound as a whole has a greater degree of symmetry than its individual components. There will be a lot more about such compounds in a future series of videos. The cube and tetrahedron don't produce anything useful. With the cube, the faces only join up after passing all the way through to form another cube, or strictly speaking, an inside-out cube. The tetrahedron faces don't join up at all. Now we'll examine the dual of the great dodecahedron. If we chop off a vertex to reveal the vertex figure, we find a star-shaped figure called a pentagram, so the dual faces must be pentagrams. A pentagram is just a non-convex pentagon with intersecting sides, 1, 2, 3, 4, 5. We're in the realm of non-convex polyhedra, so non-convex faces are perfectly acceptable. This particular pentagram has equal sides and angles, so it's a regular polygon. The great dodecahedron has 12 vertices, so the dual must have 12 faces. And its faces are pentagons, so the dual must have 5 faces at each vertex. Putting together 12 pentagrams, 5 round each vertex, we get this shape. This is the small stellated dodecahedron. Externally, This looks like it's made of 60 triangles, forming 12 pentagonal pyramids. But seeing it that way is to ignore its internal structure. The visible triangles are just parts of the larger pentagrams. Turning to the great icosahedron, its vertex figure is also a pentagram. Its faces are triangles, so its dual must have 3 pentagrams surrounding each vertex. This is the great stellated dodecahedron. These 2 polyhedra were found by Johannes Kepler in the 1600s, although they had been illustrated earlier. The 4 polyhedra I've covered are known as the Kepler-Poinsot Polyhedra. They all have identical regular faces and vertices, and so are called regular polyhedra. The Kepler-Poinsot Polyhedra are the only 4 non-convex regular polyhedra. The 5 platonic solids are also regular, making a total of 9. As always, thank you for watching. Please like and subscribe if you enjoyed it, and I'll see you next time.